Eventually, got these amazing instruments onto these vehicles to do some great exploration. The goal of Spirit and Opportunity, the official sort of proposal lingo, was to determine the aqueous climatic and geologic history of sites on Mars where conditions may have been favorable to the preservation of evidence of prebiotic or biotic processes. And the index card version is, was Mars habitable? Right? And that's essentially the same kind of goal that Curiosity has at a different place, chosen with a lot more information than we had to choose the landing sites for Spirit and Opportunity, and with a different payload. I'll come back to that at the end. Spirit and Opportunity are often referred to as robotic geologists. They are tools for geologists and mineralogists and chemists and physicists and biologists on the Earth. You've seen this before. Of course, there's a mast that's about the height of a 10-year-old kid with cameras up here. These are the cameras that I helped to work on, and we continue to work on with Opportunity for remote sensing. Solar-powered spacecraft with an arm that's capable of measuring the chemistry and touching the surface and drilling and grinding into it. So very, very capable robotic machines. One of the things that's often not remembered as a critical tool of these machines is their mobility. And this is a common theme with Curiosity now as well. These are some kind of time-lapse animations from the front hazard cameras of Spirit and Opportunity. And being able to rove, being able to traverse, to move from point A to point B has been just as critical as having cameras, as having spectrometers and other kinds of instruments. And we've used that capability enormously. You know that Spirit's mission is over, but I can give you sort of the quick overview of some of the major highlights of what we found from Spirit. We traveled inside Gusev Crater, this putative ancient lake bed, now covered with volcanic minerals, but still showing some geologic evidence of water having been there. We traveled along the yellow path, across these volcanic plains, up into some hills where we saw some evidence of watery activity, down into this valley to a place called Home Plate. And Spirit's 90-sol mission ended 2,210 sols later in March of 2010, when we succumbed to the dust on the solar panels and a couple of bum wheels. I won't dwell on this, but there's a wonderful list of scientific highlights, lots of information on the chemistry of these volcanic rocks in the plains, sort of low water-to-rock ratio alteration, lots of textures and different kinds of rock types in these hills that we went to. Some of those rocks were thrown in from impacts elsewhere on Mars. Some of them were outcropping from the formation of those hills intrinsically. Lots of different minerals discovered, hematite, goethite, carbonates, and rocks. Take the mineral test out in the hall there. You'll see some of those. Lots of volatile elements found in these hills, evidence for higher water rock alteration. And then where we ended up at the end of the mission at Home Plate, volcanic sediments, high sulfur silica soils consistent with this hydrothermal origin of this place. This area, Home Plate, was the gold mine of the mission. Thank goodness we lasted more than 90 sols, because it took us years to get to where the richest science came from, this hydrothermal alteration zone, high water rock alteration, high temperatures, by any measures, in a terrestrial standard, a habitable environment. So that was a very, very cool thing. Landed in these volcanic plains, and what a lot of people don't appreciate, I think, is that most of that science and those bullets didn't come from pictures, although, of course, I love the pictures. It's a spectacular landscape. It's phenomenally beautiful in a very alien way. Most of that science came from the squiggly line instruments on the rover's arm and in the remote sensing package, the so-called spectroscopy. And so that's how we can not just say, oh, we think that there's been water there, but we can say, look, there are water-formed minerals in that environment today. Some of that water that was on Mars is trapped in these mineral grains. It's still there. We can detect them today. So it's definitive, and that's the kind of stuff that you get published in Science and Nature magazine. So that was pretty cool to be able to make that leap from just photographic interpretation to quantitative chemistry, geology, geochemistry, mineralogy. Took the long drive across the hills here. We kept finding these very, very dry volcanic rocks, which was exciting to volcanic geologists, but not to a lot of other people. But we could see from orbit that these hills were different, so that's what compelled us to get over there. Didn't know if we'd make that that drive. Of course, the warranty ran out at the beginning of the yellow line, 90 sols later. But we did, and Spirit turned out to be just an outstanding hill climber. Being in the hills turned out to be really useful because just like hiking on Earth, the hills have breezes and wind, and that cleared the solar panels a number of times of the dust that was accumulating and allowed us to survive much longer than we would have otherwise. Heading back down the other side of the hills, past these beautiful sand dunes, and into this valley where we spent most of the mission. More than 4.5 years of the 6-odd-year mission was spent down here around this feature called Home Plate, which is about 80 meters across, roughly circular. And we think it's the eroded remnants of an ancient cinder cone or volcanic construct of some kind from a hydrothermal environment. Here's what that looks like edge on. Here's the edge of it here. It's a raised plateau, a couple of meters high, and along all the edges of the plateau, we see this just beautiful layered, very finely layered rocks. Lots of evidence of kind of frothy, volatile-rich volcanic rocks in this place, so we know it was a volcanic environment that tells us the heat was there, and beautiful evidence of layering in many parts of Home Plate, including some places where it looks like rocks were thrown up, deposited or dropped onto soft sediments that deformed. So these were warm, wet, sedimentary deposits in this kind of hydrothermal environment. And accidentally discovered just under the surface because Spirit's front right wheel stopped working a few years into the mission. We accidentally discovered these soils, which were loaded with sulfur and silica, hydrated, common hydration mineral products in hydrothermal environments like you find at Yellowstone or in Iceland or in Hawaii. And so this was pretty unexpected and also one of the biggest discoveries of the mission. So this was, by many accounts, a habitable environment, which was pretty exciting. What ultimately killed us was the fact that Mars is a dusty place and we couldn't spend all of our time up on ridges and hills. And we started off with nice clean solar panels in 2004. Here we are in 2007. Here we are in 2010. Where'd the rover go? And so that turns directly into lower solar power, and a more difficult ability to make measurements and drive. We eventually did get bogged down in an area where if we had more power and more time, we probably would have been able to come out, but dusty solar panels, setting winter sun, all of that conspired to trap the vehicle in late 2009, early 2010. You can see kind of the crusty soil that we were breaking through. We were making progress until the sun got too low, couldn't drive anymore, had to go into a hibernation mode for the winter. And in fact, this is our last color picture that came down. What a beautiful place. This almost looks like shale. There's all kinds of cool, different colored minerals in here. We had all kinds of plans to study this stuff in more detail. And despite an intense internet campaign to try to free Spirit, which I suspect many of you participated in, we didn't get out, and that mission ended in March 2010. Spirit's still there. We've seen it from the high-rise camera, from orbit. Nobody's taken it. The wheels are still on, all that kind of stuff. So it's a future. I firmly believe this is a future stop on the Smithsonian Museum on Mars. There'll be a felt rope around here. You'll have to keep your kids back off the rover, that kind of stuff. It is a human heritage site, and it will be there forever. Meanwhile, on the other side of the planet, right, we're doing this mission with Opportunity, which still goes on. And today is all 3,031 of Opportunity's 90-day mission on Mars. And we've traveled this red path, hopping from landing in a crater and hopping from crater to crater to crater, and now exploring Endeavour, which is big enough that you can actually see it in standard Mars maps, 25 kilometers or so across. And we're there because from orbit, one of the NASA orbiters sees these clay mineral deposits in this area, and we haven't seen those on the surface yet. So our goal has been to get there and study them. But each of these long trips, this is 2 years here, this is 3 years here to drive along these paths to get there. But we have made it. Here's the slide summary of what Opportunity has done, is still doing. Almost 35 kilometers of traversing, studying impact craters, Eagle, Endurance, Victoria, Endeavour, bigger and bigger craters, studying deeper and deeper into the Martian subsurface and back farther into Martian time. We see lots of evidence for basaltic sand and volatile-rich minerals, including the iron-bearing hydrated sulfate called jarosite, hematite, and the hematite occurring in these little spherical concretions that we think were precipitated from water-saturated rocks. Lots of layered rocks, laminated rocks, cross-bedding textures that all support this idea of shallow water having flowed across this area at one point in the deep past, and rinds and veins filled with minerals, including very recently the discovery of gypsum on Mars from the rover. So even though we're in our 9th year, we're still making interesting and exciting discoveries with this vehicle. Here's where we landed, a crater about the size of this room. You see the lander in here and the tracks as we drove around. One of the luckiest landings in space exploration history, because this beautiful outcrop of hydrated, sulfur-bearing, hematite-bearing outcrop sitting there waiting for us to study. And of course, the very first thing we did, driving off the vehicle, looking down at the ground, seeing this almost alien landscape, right? Covered with these small spherical grains, which we've interpreted as concretions, these little grains kind of that form like stalactites and stalagmites in a cave, precipitating out of watery solutions. And that's pretty exciting, but was it typical? So we had to find out if there are other places where we could see that kind of mineralogy, that kind of geology. So we went to Endurance Crater, which is about the size of the Rose Bowl here in Pasadena. Had the rover drivers kind of very carefully drive us around and get down, and we wanted to study these layered rocks in the slope. Very, very precarious environment, and it's really hard to imagine. This is 150 million miles away, this little robot sitting on the inside of this bowl, tilted about 20 degrees over its shoulder, taking this spectacular panorama and studying these rocks with the arm and looking at the chemistry, looking at the mineralogy. And lo and behold, we found these hydrated minerals all the way through this stack, the hematite, the concretions, the sulfates. So this watery history, converting these ancient sandstones, which had been just kind of volcanic sand, the water comes up, recharges the environment, alters the minerals, forms other alteration products, leaves some of that water in the minerals, and then goes away, probably multiple times. So it was a warm and wet environment compared to what it is today. And that's kind of exciting, but is it typical, or did we just happen to land in this one freaky little spot? Well, let's go down to this bigger crater, right? So we took 2 years to drive down there, eventually getting down to Victoria, which is more like the size of a college campus. Okay, a big hole in the ground with, again, lots of precarious driving, difficult situations we had the rover up here for a little while, basically studying these alcoves and promontories, arriving in September 2006, looking for a good way in, driving around for several months on these alcoves and promontories, measuring the slopes, hoping to get in, finally saying, oh, you know what, the best place to go in was here. So turned around, came back, went back in. And it turned out we couldn't get in very far. The slopes are pretty steep, and if we get too far down, we end up in this rover death trap, this big pile of sand dunes in here. So we only went a little ways in. But we went far enough in to look at the layered rocks and take, not only some just spectacular photographs. That's Steve Squire's rock hammer, by the way. But allow us to measure the chemistry of a lot of these materials as well. And so these layers that you can see in cross-section here, there's no way we could study these kind of things directly with the rover. But on these gentle slopes, they're exposed in outcrop in plan view. So we could drive over these brighter deposits and say, oh, that's the same layer that we're seeing here, and map that all around the crater. And again, we saw the hydrated minerals, the hematite, the sulfates, all the way down in this stack. So this aqueous history was extensive in this part of Mars. What's frustrating is that we can't tell you how long it lasted. We have no tools on the rover to do age dating. It is one of the tools that if I'm a geologist, I go out in the field and I want to study, particular outcrops or whatever, I go collect samples, or my graduate students would go collect samples, bring them back to the lab, and we do some age dating on them. And you could say, well, there's 10 million years between this layer and that layer. We can't do that. And it's a big missing piece of the field kind of study that we do on Mars. But we know that this is an ancient place. We can tell just from the number of impact craters in the area that this is an ancient environment. So we finished up our work at Victoria and headed down on that long 3-year trek to the rim of Endeavour Crater. This is the end of the 3-year trek just last fall. We got to one piece of, so this is the piece of the rim of Endeavour. It would be, you know, like would fill the entire room if we drew the whole thing. One piece exposed here that was closest to us. Got to it and have been driving across this ridge. So this is ancient Martian terrain compared to the plains here, which is also very, very old, but this is even older. And it's part of the rim of this ancient impact crater. We know from orbit that these clay signatures are all on the southeast side here. And as we got up to here, the winter was starting to set in. And because of the latitude we're at, we need to keep the solar panels tilted into the sun. And so we could not go on the south side because that would tilt us the wrong way. Our power levels would drop. Opportunity is getting dusty as well. Our power levels would drop. We wouldn't survive. So we had to stay on this northwest facing slope, find a good place to tilt ourselves into the sun. And so we did that. Along the way, we found some beautiful examples of veins. This image is about 40 centimeters across. So this is just 1.5 centimeters, so less than an inch wide, little vein, and lots of places around here with veins running through it. And these are filled with gypsum from water in the subsurface running through cracks created by the ancient impact event. And the cool thing about gypsum, it's a sulfate, it's a hydrated sulfate, but it forms in neutral or high pH water preferentially. If this was low pH water like we'd seen with the jarosite elsewhere, then that stuff would dissolve into solution. Well, that didn't happen. It's still there, and it's old, so it's telling us something changed in the environment from sort of neutral to alkaline water to more acidic water. And we're studying that boundary of where that happened in this area. So that's a pretty exciting thing. So I mentioned we had to stop and park, and while we parked, we took a big 360-degree panorama, waiting for the winter sun to get higher. We used the arm to study all kinds of rocks and minerals around us. We just passed the winter solstice a few months ago. The sun is getting higher. Our power levels are getting higher. We had a magical wind clearing event just a few weeks ago. Poof, the power jumps up again. I wish we could take credit for that, but that's just Mars being nice to us. So we left our parking spot, and now we've been driving along this line, and today we're at this place called Wim Creek, and we're studying this boundary between the older, more neutral pH kind of environment and the slightly younger, lower pH environment. And so here's, let's see if I can pull this up. There we go. This is just fresh in. Some images that were just taken on Wednesday that just got downlinked last night. So here's that crack in the surface that we're looking at. And so we're making chemical and mineral measurements all along this area because that natural fracture has kind of given us a free little road cut into this boundary between these two key times in Mars history. So very, very exciting. We still have not found the clays, and our plan is to continue to drive around. Now that the sun is getting higher, we can go around to the southeast side and find the surface expression of those clays. We don't know what they look like on the ground. It's one of the few minerals that we know is on Mars we haven't seen on the ground. You know, nobody predicted that hematite would come out in these little spherical grains. What's the clay going to look like? And we have kind of a fun little contest, a little competition going on between us and the Mars Science Lab team because they're going to land, we're going to land Sunday night, all of us, in an area that also has clays. So who will see them first? That's going to be kind of exciting. And will they be the same? Just a few more minutes then, talking about MSL, about Curiosity. And again, the sort of textbook goal is to explore and quantitatively assess a local region on Mars' surface as a potential habitat for life, past or present. And that's very, very high level. A little more specifically, it's all about biologic potential, geology, geochemistry, the role of water, and looking at surface radiation to feed forward to... why don't you hold your questions to the end, please? We'll feed forward to human exploration. Sorry, I'm just trying to get through this really quick. Comparing Spirit and Opportunity to Curiosity. Curiosity has more instruments. It is a much more complex system. It is a larger rover, twice the size, about 3 times the mass. There are color cameras and navigation cameras up on a mast that's about 2 meters high. There's an arm that's much larger that has a microscope, chemistry, a brush, and a drill, and it'll scoop up samples to grind and scoop up samples to bring them into the rover to do detailed organic chemistry with the chemistry and mineralogy instruments that are built inside. So it's a much, much larger vehicle. Surprisingly, moves at the same speed as Spirit and Opportunity, about 4 centimeters per second. But it's designed for 1 full Mars year. So the manufacturer's warranty from our friends at JPL is 1 full Mars year on this one. So you can do the math, right? Spirit and Opportunity were designed for 90 sols. They live several thousand. So how long is Curiosity going to last, right? Your grandchildren will be driving this rover. And driving is absolutely key. Driving is the key to this mission, just like it has been with Spirit and Opportunity. We have this amazing mobility system. We're landing in Gale Crater. I'll talk about that in a moment, in a very safe place, but we want to drive to a much more interesting place, and we have to make that drive. It's what the scientists call a go-to site. Yes, it scares the hell out of me that we're landing on those wheels, okay? But I'm telling you, I think all of us should just have blind faith in our engineering friends. They're going to get us there. I know these men and women have spent years of their life building the best possible system, and they're going to get us down there safely. But yes, it scares the hell out of me that we're landing on the wheels that we need to go 10 kilometers to get to the cool stuff. And where we're going is Gale Crater. We're landing roughly here on the star. It's 150 kilometers across. It's right on the boundary between the ancient highlands and the younger lowlands of Mars. And one cool thing about this crater is this huge pile of sediments in the middle. And the top of this pile actually goes higher than the rim of the crater in some places. And so this crater was entirely filled by sediments, brought in by water, brought in by wind, and then it's been excavated, it's been dug out, it's been exposed to us. It's a free road cut of the history of Mars, and this 3D view shows the area that we'll be driving into. So we land in a relatively flat, safe place, drive across these sand dunes into this kind of terrain. And these layered deposits are sampling different eras in Mars history, from the ancient so-called Noachian, 4.2 billion years ago, and we'll drive up. And if we choose to drive all the way to the top, if we survive that long, then what's up there is dust falling on the thing today. So you've got the entire stack of Mars history in one place. It's like going to the Grand Canyon, starting at Phantom Ranch, taking your rock hammer and your backpack with tools, and walking up the section. It's what a geologist, a sedimentologist would do on the Earth. And along the way, we've got all kinds of cool minerals. The geology is spectacular. The landscape is going to be beautiful. It's going to be evocative of the desert Southwest, I'm sure of it. Mesas, canyons, mountains. It should be an absolutely spectacular place. And there's all these kind of cool minerals up here that are marking different changes in the Martian environment, the geology and the chemistry and the mineralogy. And we're going to study that like reading the pages of a book and trying to put the picture together, trying to put the puzzle pieces together of what ancient Mars was like and how habitable was it. So just in last slide here, I'll invite you all to follow along with some websites where we put a lot of pictures and MSL information. That you've seen the cool video. I'm sure you'll see it 20 times this weekend. And just remind you that you guys and the Planetary Society are part of something bigger, that we do have a responsibility to share our passion for space exploration with our elected representatives, with our neighbors, with our kids, with their teachers. Okay? This is our job, because we need to do what Robert was talking about. Okay? We need to get this country charged up about exploring space. It's one of the coolest things that we do. It's one of the most inspirational and educational things we do. As a taxpayer, I'm proud to support it. Okay? You should be too, and your neighbors should be too. So get out there, tell that story. Thank you. Time for some questions? A couple of minutes for questions. There's somebody who had a question, it was a burning question here. Yes.
Speak up,
I can't hear you, I'm sorry.
One thing that's misleading, Mars is not habitable by humans. There's a very bad radiation atmosphere in Mars which you didn't refer to. And it's due to the fact that Mars has no magnetic field that the Earth has. And that radiation is deflected to the Earth and allows us to live for 80 or 90 years. We're not too sure how long now.
Sure. No, it's a totally valid point, but I would agree with what Robert said. We can overcome that.
No, you can't.
Next question. Yes, sir.
From what the scratches you've made on Mars, how would you say it's most